Electricity is a fundamental force of nature and a cornerstone of modern technology. To understand electrical concepts and applications, it's essential to grasp the basic principles that govern the flow of electrical energy. Let's begin with the fundamental quantities voltage, current, and resistance. Voltage, often described as electrical potential difference, is the driving force that pushes electrons through a conductor. It's measured in volts. Think of voltage as the pressure in a water pipe. The higher the pressure, the more water flows. Similarly, the higher the voltage, the more electrons flow. Current is the rate of flow of electrical charge. It's measured in amps. Imagine current as the amount of water flowing through the pipe. The more water flowing, the higher the current. Resistance is the opposition to the flow of current. It's measured in ohms. Picture resistance as a constriction in the water pipe. The narrower the constriction, the more resistance there is to the flow of water. The relationship between voltage, current, and resistance is described by Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms. This simple equation is a cornerstone of electrical circuit analysis. It allows to calculate any one of these quantities if the other two are known. For example, if a circuit has a voltage of 12 volts and a resistance of 6 ohms, the current flowing through the circuit will be 2 amps, which is 12 volts divided by 6 ohms. Power is the rate at which electrical energy is transferred or consumed in a circuit. It's measured in watts. Power equals voltage times current. So, in the previous example, the power dissipated in the circuit would be 24 watts, which is 12 volts times 2 amps. Understanding these fundamental concepts is crucial for analyzing and designing electrical circuits. Now let's delve into the different types of electrical circuits. There are primarily two types of circuits: series circuits and parallel circuits. In a series circuit, components are connected end-to-end, forming a single path for current flow. The current is the same through all components in a series circuit. However, the voltage is divided across the components, with the sum of the voltage drops across each component equaling the total voltage applied to the circuit. The total resistance of a series circuit is the sum of the individual resistances. For example, if you have 3 resistors connected in series with values of 10 ohms, 20 ohms, and 30 ohms respectively, the total resistance of the circuit would be 60 ohms. In a parallel circuit, components are connected side by side, providing multiple paths for current flow. The voltage is the same across all components in a parallel circuit. However, the current is divided among the branches, with the sum of the currents in each branch equaling the total current entering the circuit. The total resistance of a parallel circuit is calculated using the reciprocal formula: 1 divided by the total resistance equals 1 divided by the resistance 1 plus 1 divided by the resistance 2, and so on. For example, if you have 2 resistors connected in parallel with values of 10 ohms and 20 ohms respectively, the total resistance of the circuit would be approximately 6.67 ohms. Another important concept in electrical circuits is grounding. Grounding provides a return path for current in case of a fault, helping to protect people from electric shock. Grounding is typically achieved by connecting the metal chassis of an appliance or electrical equipment to a grounding electrode, such as the ground rod driven into the earth or the metallic water pipe entering a building. The grounding system provides a low impedance path for fault current to flow back to the source, causing a circuit breaker or fuse to trip and to energize the circuit. Electrical safety is paramount when working with electricity. It's crucial to take precautions to prevent electric shock and other hazards. Always to energize circuits before working on them by turning off the circuit breaker or removing the fuse. Use insulated tools and wear appropriate personal protective equipment, such as rubber gloves and safety glasses. Never work on electrical equipment in wet or damp conditions. Be aware of the potential hazards of overhead power lines and underground cables. Maintain a safe distance from power lines and coal before you dig to locate underground utilities. Regularly inspect electrical cords and appliances for damage and replace them if necessary. Ensure that all electrical outlets and appliances are properly grounded. Use ground fault circuit interrupters, or GFCIs, in areas where there is a risk of water exposure, such as bathrooms, kitchens, and outdoor outlets. GFCIs are designed to detect ground faults and quickly interrupt the circuit, preventing electric shock. Electrical systems in buildings typically consist of several components, including the service entrance, distribution panel, branch circuits, and outlets. The service entrance is where the electrical power enters the building from the utility grid. It includes the meter, which measures the amount of electricity consumed, and the main disconnect, which allows to shut off power to the entire building. The distribution panel, also known as the breaker box, is the central hub for distributing electrical power to the various circuits in the building. It contains circuit breakers that protect each circuit from overcurrents. Branch circuits are the individual circuits that supply power to lights, outlets, and appliances. Each branch circuit is protected by a circuit breaker in the distribution panel. Outlets are the points where electrical power is accessed to plug in lights, appliances, and other electrical devices. There are different types of outlets, including standard 120 volts outlets, 240 volts outlets for larger appliances such as dryers and stoves, and USB outlets for charging electronic devices. Wiring methods used in buildings vary depending on the type of construction and the local electrical codes. Common wiring methods include non-metallic sheath cable, also known as Romex, which is typically used in residential construction, and metallic conduit, which is often used in commercial and industrial construction. Non-metallic sheath cable consists of insulated conductors bundled together within a plastic jacket. Metallic conduit is a rigid or flexible metal tubing that protects the conductors from damage. Electrical codes and standards, such as the National Electrical Code, or NEC, provide detailed requirements for the safe installation and maintenance of electrical systems. The NEC is a widely adopted standard in the United States that sets the minimum requirements for electrical installations. It covers topics such as wiring methods, overcurrent protection, grounding, and equipment installation. Local electrical codes may also have additional requirements that are specific to the region. It's important to be familiar with the local electrical codes and to follow them carefully when working on electrical systems. Now let's talk about some common electrical components. Resistors are components that oppose the flow of current. They are used to control the current in a circuit or to provide a voltage drop. Capacitors are components that store electrical energy in an electric field. They are used to filter out noise to smooth voltage fluctuations and to store energy for later use. Inductors are components that store electrical energy in a magnetic field. They are used in filters, transformers, and other circuits. Diodes are semiconductor devices that allow current to flow in only one direction. They are used in rectifiers, voltage regulators, and other circuits. Transistors are semiconductor devices that can be used as switches or amplifiers. They are used in a wide variety of electronic circuits. Integrated circuits, or ICs, are complex circuits that are fabricated on a single silicon chip. They contain millions or even billions of transistors, resistors, and capacitors. ICs are used in computers, smartphones, and other electronic devices. When troubleshooting electrical problems, it's important to follow a systematic approach. Firstly, identify the problem. What is not working properly? Secondly, gather information. Check the circuit breaker, look for loose connections, and inspect the wiring for damage. Thirdly, analyze the circuit. Use a multimeter to measure voltage, current, and resistance. Fourthly, test the components. Check the resistors, capacitors, diodes, and transistors. Fifthly, repair the circuit. Replace any faulty components and make sure all connections are tight. Electrical safety is paramount when working on electrical systems. Always to energize the circuit before working on it. Use insulated tools and wear appropriate personal protective equipment. If you are not comfortable working on electrical systems, call a qualified electrician. Let's examine some practical applications of electricity in Northern Illinois. Many industries in Northern Illinois rely heavily on electricity to power their operations. Manufacturing plants use electricity to run machinery, assembly lines, and lighting systems. Data centers, which are critical for storing and processing information, require significant amounts of electricity to power servers, cooling systems, and backup generators. Hospitals and healthcare facilities depend on electricity to operate life support equipment, diagnostic imaging systems, and other essential medical devices. Commercial buildings, such as office buildings, retail stores, and restaurants, use electricity for lighting, heating, air conditioning, and powering various appliances and equipment. Electricity also plays a vital role in transportation in northern Illinois. Electric trains and buses are becoming increasingly common, reducing reliance on fossil fuels and lowering emissions. Electric vehicle charging stations are being installed throughout the region to support the growing adoption of electric cars. Furthermore, agriculture in northern Illinois relies on electricity for irrigation, lighting, and powering farm equipment. Renewable energy sources are playing an increasingly important role in the electricity supply in northern Illinois. Solar power, wind power, and biomass energy are being developed to reduce reliance on fossil fuels and to create a more sustainable energy future. Solar panels are being installed on rooftops and in solar farms to generate electricity from sunlight. Wind turbines are harnessing the power of the wind to generate electricity. Biomass energy, which involves burning organic matter such as wood and agricultural waste, is being used to generate electricity and heat. Smart grids are being developed to improve the efficiency and reliability of the electrical grid in northern Illinois. Smart grids use advanced technologies such as sensors, communication networks, and data analytics to monitor and control the flow of electricity. They can help to reduce energy waste, improve grid stability, and enable the integration of renewable energy sources. Energy efficiency programs are being implemented to reduce electricity consumption in homes and businesses in northern Illinois. These programs provide incentives for customers to upgrade to energy-efficient appliances, lighting, and insulation. They also offer educational resources and technical assistance to help customers reduce their energy bills. Emerging electrical technologies are being developed in northern Illinois, including microgrids, energy storage systems, and advanced power electronics. Microgrids are small-scale power grids that can operate independently from the main grid. They can provide reliable power to communities, businesses, and critical facilities during power outages. Energy storage systems, such as batteries, are being used to store electricity generated from renewable energy sources. They can help to smooth out the intermittency of renewable energy and to provide backup power during emergencies. Advanced power electronics are being developed to improve the efficiency and control of electrical power conversion. They are used in a variety of applications, including electric vehicles, solar inverters, and industrial motor drives. Electrical safety is a critical concern in northern Illinois. The local electrical codes and standards are enforced to ensure that electrical installations are safe and compliant. Electrical inspections are conducted to verify that electrical work is performed according to code. Electrical safety training programs are offered to educate electricians, contractors, and homeowners about electrical safety practices. Electrical hazards, such as damp power lines, overloaded circuits, and damaged electrical equipment, are addressed promptly to prevent accidents. Here are some tips for saving energy at home. Firstly, switch to energy-efficient lighting. Replace incandescent light bulbs with LED bulbs, which use up to 75% less energy and last much longer. Secondly, unplug electronics when not in use. Many electronics continue to draw power even when they are turned off. Thirdly, adjust the thermostat. Lower the thermostat in the winter and raise it in the summer to reduce heating and cooling costs. Fourthly, seal air leaks. Seal cracks and gaps around windows and doors to prevent air from escaping. Fifthly, insulate your home. Insulate the walls, attic, and floors to reduce heat loss in the winter and heat gain in the summer. Sixthly, use energy-efficient appliances. When purchasing new appliances, look for the Energy Star label. Seventhly, wash clothes in cold water. Washing clothes in cold water can save a significant amount of energy. Eighthly, limit shower time. Reducing the length of your showers can save water and energy. Ninthly, run the dishwasher and washing machine only when they are full. 10thly, air dry clothes when possible. Air drying clothes can save energy and reduce wear and tear on your clothes. Understanding these electrical concepts and applications can empower to make informed decisions about energy usage and electrical safety. By adopting energy-efficient practices and taking precautions to prevent electrical hazards, individuals and communities in northern Illinois can contribute to a more sustainable and safe energy future.